welcome everyone. Thank you for joining us on this Friday afternoon. I'd like to begin by acknowledging that the traditional owners of the land on which we're all meeting throughout the country. Here in Perth, I'm meeting on the land of the Whadjuk people of the Noongar Nation, pay my respects to their elders, and do that on behalf of all of us around this wonderful country. In terms of the size and scope of our country, we also operate across different time zones. And I think there might be a number of you that were very keen to join this session a couple of hours ago and dialed in at East Coast time. So thank you for your patience and coming back if that's the case. I think we had 50 or more people join in a couple of hours ago. We are clearly very pleased to support this initiative through Pawsey and bring together an expert panel for you on Friday. This event, we're looking to cover Australia's quantum landscape and really explore the roles and opportunities for SMEs, corporations, governments, universities and investors. And for Pawsey, this builds upon the partnership that we've established with Quantum Brilliance, and you'll hear from them through this presentation. But they're an Australian quantum computing company using novel technology to develop quantum computing at room temperature, and really part of the vanguard of advancing Australian quantum computing. So we're happy to partner with Quantum Brilliance and really look at developing the expertise in our centre as one of the two national supercomputing centres, Tier 1 supercomputing centres. And it's part of our plans to develop, in partnership with Quantum Brilliance, access to a quantum emulator and really support engagement and innovation around that technology. But during this particular event, you're going to hear from the panel of experts that will explore the national quantum computing landscape, opportunities for quantum computing in industry, the national quantum computing industry roadmap, and also the pathway forward for generating a really healthy quantum innovation community and industry. And based on the level of interest in this program, we're really pleased to see the level of potential and momentum that's been generated around quantum. I'd like to thank my colleagues for supporting this initiative and acknowledge all of the participants and partners and support that Pawsey has from the Australian Government, the West Australian Government, our university partners and CSIRO, and thank them for their contribution. Pawsey is going through a really exciting time. We're right in the middle of a significant capital upgrade. So we're upgrading our major systems. So look forward to announcing the next generation of supercomputing infrastructure at Pawsey in only a matter of weeks. Sometime in September, we're hoping to announce that major investment decision. So watch this space and look forward to communicating that to you soon. I'd also like to put a shout out for gender equity and acknowledge that it's sort of wearing it purple sort of week this week and day today. I've not done a very good job of purple, but I do have my pin and acknowledge the disparity in the equal pay issue today. And in fact, in Western Australia, we've got the greatest disparity in terms of the gender pay gap. And so there's still a lot of work to do on that front. With all of that, I'll hand over to my colleague, Ugo Veretto, who's the Chief Technology Officer for Pawsey and leading our technology strategy. And he's going to introduce our presenters. And so thank you again, and over to you, Ugo.
Thank you very much, Mark. Yes, so we're going to start with the presentations. I'm going to introduce our first presenter, Dr. Cathy Foley. Dr. Cathy Foley is a chief scientist with CSIRO, Australia's National Science Agency and Innovation Catalyst. Dr. Foley has made significant contributions to the understanding of supercomputing materials and to the development of devices using superconductors to detect magnetic fields and locate valuable deposits of minerals. Seeking to start a conversation between government, researchers, and industry on the benefit of quantum technology to Australian industry, Dr. Foley recently launched the Quantum Roadmap report. So, Cathy, whenever you're ready.
Okay, thanks very much. I'm just going to get things going. Got to press a few buttons. So here we go. And is that right? And then go through and get that into the right mode and get it so that it's in the right slot. There we go. So thanks everyone for coming along today, because this is a really exciting area for me. And the reason it's exciting is that quantum was something I've been working in for over 30 years. And for a long time, everyone saw it as a laboratory curiosity. But I can see now it's going to be ubiquitous, and especially in Australia, it's going to touch every one of us. And I hope by the end of this talk, it will convince you that that will be the case. So the quantum technologies in Australia are amazing, and we're world leader in many, many technologies that are being adopted. In May this year, we launched a collaborative piece of work across all the research in quantum technologies across Australia, where we looked at how we could grow Australia's quantum industry and created a roadmap using the CSIRO's futures process to look at is there a market there? Is it something we should be doing? And if so, what should we do? And it's, from my perspective, it's exciting that researchers want to take their science out of the lab and turn it into impact. And today you'll hear from a number of startup companies that have exactly done that. And I know that one of my passions is to support that. And I know from CSIRO's perspective, that's absolutely what we're trying to do. So if you look at quantum research and development in Australia, we've got a lot of it, and it's world class. We've been as a nation, working in quantum technologies, a lot of it funded by the Australian Research Council with many centres of excellence, many discovery grants. But more recently, we're seeing multinationals such as Microsoft, Rigetti, and IBM actually coming to Australia and setting up research here. And we're also seeing a whole lot of startup companies coming as well out of this. So the idea is, with this, I guess, promising growth of opportunities, is the creation of new markets, new applications, and from our perspective, seeing new jobs, which probably those of you are probably sick of hearing jobs of growth as being important, but it is important in any nation to be able to be successful and sustainable. So the commercial applications of quantum systems and technologies are broad, and at the moment I'm being looking at not just computing, but also sensors and communications. And these technologies can be in, for example, accelerating drug discovery, materials development in healthcare. For example, if we'd had quantum computers, chances are we would have been able to get to a vaccine much faster. And we're already beginning to see in silico design of materials as something which was really accelerating. And with the advent of quantum computing, I think we will see another step up. We've also seen from our Department of Defence and Defence Science and Technology group of Defence launching their star shots, of which one of them is quantum based. And that's because we can enhance our national security and support our defence, but also in communications and a whole range of other areas as well. We can also increase our productive mineral exploration and water resource management for mining and other sectors, and that's the area I've worked in. I'll share a little bit of that in a sec. And we can also improve secure communications for industries like space, but also telecommunications and for the financial sector, to just name a few. So just to let you know that I have a little bit of track record in quantum technologies and what it takes to commercialize them. So back with the discovery of high temperature superconductors in the late 80s, I was part of a team in CSIRO that took making a very difficult material, which is a ceramic, into an electronic device that can detect very small magnetic fields. And working with BHP, we developed a system called LANTEM, which can detect mineral deposits down to more than a kilometre deep in the earth. What you're seeing there is the long and laborious, decade-long effort to take a device which was done before the 1990s to a system which could be packaged and then taken out to the field with various embodiments as we learnt along the way, to get to a point where we had mineral exploration where it starts, first of all, looking at an open field like that but being able to detect ore bodies, so that one of the things which was our first major breakthrough was helping BHP to delineate the Caddington silver mine, so that they were able to bring that on board 18 months earlier than if we had not been involved. So it just sort of highlights the potential impact that one particular system can have on a whole industry. And we've now got to a point where Landtem is commercialised, it's got a life of its own, and we only know what's happening with it because we occasionally look up on ASX announcements where mining companies announce that they've used Landtem to discover yet another mineral deposit, and it's discovered billions of dollars of mines around Australia and in Canada and in South Africa. But that's not the only application. This is something that came from IBM last year, where they went through showing that particularly quantum computing, and I'm just going to focus a little bit more on that now, has the potential to have extraordinary impacts on just about every industry. So I've got chemicals and petroleum, distribution, logistics, financial services, healthcare, life sciences, and manufacturing. And there's a whole range of different algorithm families, which I won't go into, that are listed there. But as you go through Horizon 1, Horizon 2, Horizon 3 areas, you can see that there's quite a range of ways that quantum algorithms and technologies can really impact so many application areas. And this is why it's going to, I think, in time, and I hope soon convince you, will be ubiquitous and become just a new norm. It's not as though Australia is the only place that's, that is undertaking research in quantum technologies. It's a very competitive and very exciting field of research. And I think if we are going to be able to capture what we've found from the roadmap to be about, for Australia, about $4.5 billion market by 2040, we really, and also create about 16,000 new jobs, which is what our roadmap identified. We really need to make sure that we capture this potential and don't let it go, as we've done with other opportunities in the past. And I get a sense that Australia's really developed and matured since days when we've missed, say, from the first quantum revolution with electronics. I think we're really seeing an interest and an opportunity for us to realise a quantum technology industry in Australia. But as I mentioned, it is competitive, and these are numbers from investment late last year. And you can see that Australia has a modest investment. It's not insignificant, but it's still modest. And then just recently, there's been indication that China has invested about $10 billion this year into, I'm not sure over what time frame, but even so, it's a big investment, and that's going to really see the potential of quantum technologies and quantum computing in particular may become available and commercial much faster. But to maintain our leadership and capture this opportunity, we've created this national conversation about coordinating what we do, having a collaborative approach, and growing our domestic quantum economy. And that's what that's all about. I might just add, just today, I'm not sure what the date is today, but on the last day or two, the Trump administration's just announced that they're investing $10 billion into advancing quantum industries. And so they're really upping this. That's just a cut and paste from a web-based announcement just from a day or so ago. So this is really a hot area, just not in Australia, but internationally. And as we fast forward to where we are today, there's lots of exciting work underway that's put Australia in a good position to capture when I talked about Australia's $4.5 billion opportunity, the worldwide opportunity is about $86 billion of projected quantum technology global market by 2024, so it's not that far away. Australia is home to some of the top quantum technology companies and in the world, and we're lucky enough to hear from some of them today. But some examples of companies are Quintessence, which is one of the first quantum company that was set up. It's a quantum enhanced cybersecurity solution. It came out of ANU in about 2007. I've also got from University of New South Wales, led by Michelle Simmons, a unique quantum computing technology company called Silicon Quantum Computing, which has been seriously invested by Telstra, Commonwealth Bank, New South Wales and federal government. And it's really making great inroads. The quantum technology for quantum industry or medical imaging is from Macquarie University with Lucigen, which just received a large grant recently, I think, from New South Wales government to take themselves to the next level. And then in South Australia from University of Adelaide, precision timing devices for diverse applications in their cryo clock company. And then probably one which is from Sydney University's Q Control, and that's looking at quantum computing and sensing for defense and other applications, deploying the ability to control the quantum engineering so that you're able to manage errors and optimize outcomes. And Q Control, run by Michael OBrien, was last year identified as one of the top 10 startups in the world, which is pretty exciting, and you might hear more about that later on. So you can see we have a strong research base and a strong innovation base.
5 minutes, Cathy.
What's that, sorry?
5 minutes.
Okay, fine, I'm nearly finished. So the roadmap is looking at having a vision for having a consensus view, that we want to make sure that we've undertook an economic analysis to determine what the availability of the opportunity is. And also we've been looking at what we need to do to make sure we have that happening. So what we've done is worked out a way forward with a roadmap on how to have a way of creating this sustainable industry in Australia. And you can go to the website to be able to download the roadmap. But what it's basically said is that there's great opportunity commercially with revenue of about $4 billion, 16,000 jobs by 2040. So it's a long way off, but we still need to keep investing. And you can see the different breakdown there in quantum computing, sensing and measurement, and communications. I won't go into the details of how we came up with the assumptions to do that, but if you ask questions, I can answer that. The actions from this are that we're going to focus and coordinate our efforts, that we're going to build the workforce, that we're going to make sure that we have productive collaborations, both locally and with international partners, and that we also create the readiness of government, society, and end users to make sure we're able to embrace quantum technologies and make sure we've got all the regulations and policies in place. So progress so far is that we've created a level of preparedness. So quantum computing is expected to disrupt cryptographic algorithms, putting at-risk digital systems and security in key industries like financial services. We saw social media creep up on us, and we're still trying to catch up, and we want to make sure that we're better prepared for a quantum revolution. We've also got the beginning of translation hubs happening, and for example, at a CSIRO site at Linfield, we are beginning to see some quantum startups coming onto the site to be able to make the most of that interface between scale up in research and access to what's needed to really get from the lab into commercialization, particularly for deep tech. And we're seeing definitely the formation of networks which are just happening, and a number of different programs or groupings of people interested in different aspects of quantum are all coming together, and this is something which we're trying to make sure is coordinated and all working together. So what does this mean for you? Well, Samsung recently announced its 5G smartphone, which actually has a random number generator in its chipset in its new phone for enhanced cryptography. So you can buy that now, and then we've also got the development of hybrid quantum computers with high performance computing systems. And this is something just taken from a recent website, just looking at what's available and how there's the potential of linking in high performance computers to quantum computers and quantum annealers. Just to let you know that there's sort of two dominant approaches for practical quantum computers. I won't go into the details, but the quantum gate ones are the circuit model of the sort of things which are qubit based, like the Silicon quantum computer, the IBM one. And then there's quantum annealing, which is an adiabatic quantum computing, and that's the DWave one. They're pretty much the same. There's some arguments about whether they are comparative or not, and One of the papers I read recently said that they were. I'm not sure yet. It's one of those great physics questions, something to discuss. But the DWave quantum computer is a company that sells, builds and makes things available. And what they're doing at the moment is looking at a whole range of optimization processes. And there's just a long list of things that their computer can do. So just to finish up, I said that can quantum computing and technologies become ubiquitous? Well, the fact that you can buy for your baby a quantum computing series of a whole lot of books on quantum, but quantum computing for babies suggests that it already is. So thanks very much.
Thank you very much, Katie. Very interesting presentation. We do not have a Q&A session right now, so we'll have to defer conversation to later on. So I'm going to introduce our next speaker, Mr. Sean Wilson. Sean Wilson is an accomplished serial entrepreneur, most recently the founder of quantum software company QXBranch and systems engineering company Shoal Group. QXBranch, founded by Sean, was recently acquired by Rigetti Computing in July 2019. QXBranch is a spin-out directly from Shoal in 2014 and has garnered major brand name clients worldwide across the finance, insurance, cybersecurity, biotech, energy, sports, and pharmaceutical sectors. Shoal Group is one of Australia's leading systems engineering company, and Sean also sits on a range of boards, including Space Industry Association of Australia. So Sean, please go ahead with your presentation whenever you're ready. Thank you.
Thank you very much, and good afternoon, everyone. Can I be heard?
Yes, yes, you can.
Excellent. All right, thank you very much. All right, well, without further ado, we'll crack right on. So thank you, Cathy, for your long perspective on the the growth of quantum. I'm going to give, I suppose, an industry perspective or a commercial perspective on it, which does in fact overlap a little bit with what Cathy said, and that's nice to know that I'm not off on my own. And so quantum computing for industry growth. So we'll look at where we've been in recent years, not right back, but in recent years, and then what the results sort of are, and or what our learnings are, including what pathways for the future and some limitations and constraints. And then and then I'm going to provide you an example of where it might go that's pretty close to some of the work that I'm involved in. All right, I won't dwell on that. My thunder has been stolen, so we'll just sort of move on. All right, now this is a useful, I use this slide quite a bit. We are in what's called the noisy intermediate scale quantum, the NISQ era of quantum computers that don't work very well, frankly. A little bit like the early days of the motor car, where yep, the theory was pretty good, but the materials wasn't particularly good, the fuel wasn't particularly good, and there was a lot of breakdowns and a lot of, if you're trying to take a long journey, a lot of noise, frankly. And so that's the equivalent of sort of where we are now. And you can see here, we're just at the start of the sort of the near-term applications, depending on sort of who you ask, because there's some debate about whether the applications that have been shown in the press in the last sort of year or two are actually practical. You can do it, yes. Is it commercially useful? Yeah, maybe. Full utility, maybe a decade away, and that's still that debate's a little bit sort of ongoing about when that will be. Perhaps someone will make a technical breakthrough next month, and within a year, we'll have a quantum computer that can do amazingly useful things. I don't think that's quite going to happen, but it's possible. And then between getting from, and this is an important point, getting from where we are now to where we want to be in predicted to be a decade's time, we're living with the early days of the motor car, where if we want to own a motor car, it's pretty good fun and it's better than a horse-drawn cart, but you've got to expect to carry some spare parts with you and know how to fix the car and know how to drive something that's a little bit delicate, unlike the cars of today, where you can pretty much get in and drive them and not worry about any of that. It's all abstracted away, and we'll cover abstraction as an issue a little bit later on. All right, so early work. Let's explore the building blocks. some early research applications, both from around the world and some work that that QBranch was involved in a little while ago. As it grew from its experimental beginnings in 2012 with when it was part of Shoal, when collaborating with Lockheed Martin, until where it is in the last year or two. Discrete portfolio optimization. In one particular case, we did enough work that we could take foreign exchange pairs, and we could optimize those better than the client bank's existing systems could. In fact, significantly better than they could, to the point where we were showing them which clients were losing them money and maybe who they should not have as a client anymore. Hard optimization using annealing techniques for multi-vehicle logistics, the classic traveling salesman problem, and cybersecurity graph analysis. We had one of our staff do a thesis on quantum computational fluid dynamics. Shoal originally is a hardcore aerospace company and still has quite a lot of work in the aerospace field, especially in modeling and simulation. And so quantum CFD is something that we could really use when it's mature. Predictive model work for regression analysis, for high speed, highly complex regression analysis. Also a lot of work on, and this is still going on today, a lot of work on benchmarking and characterization of quantum computing. We need to understand the various architectures and how they perform and their strengths and weaknesses and where they might go. Right now, companies are making significant investment decisions. And if you look at the, and I haven't got I could have had, but I don't have a lot of slides on this one. If you look at the various architectures being promoted by the major firms around the world of Google, IBM, etc., they're quite different. They're quite different at the concept being promoted, and at some point we would expect, like in the early days of the motor car and the aircraft, that all those different architectures will probably settle down to between 1 and 3 stable ones that then go on to be the basis of everything that follows. And that certainly happened in computing, the Neumann architecture of today, for example. One thing or a key to what we're doing is simulation. The reality is that up until relatively recently, we didn't actually have any real working quantum computers. We've had access to, DWave Corporation's been around for quite a while, and their computers have been working since about 2012. Are they practical and can they solve commercial problems? Maybe now, but certainly not then. And how do we explore that? Well, we explored that with simulation. And so building good simulation and good emulation is critical in our view, or my view, to the progression of the quantum computing field. Until these architectures stabilize and until they become affordable, although some of them are starting to come in on the cloud now, so that argument's maybe diminishing a little. So what have we learned in the last few years? Probably 5. I've got a report that suggests that there's five algorithms, 5 methods that show real promise for early practical application. One is Shor's algorithm. Many of you would have heard of Shor's algorithm, which is about factorizing integers and prime numbers, very, very good for cryptography and the like. Grover's algorithm, searching an unsorted database. In a world of big data, effective and time-efficient search is critical to many operations. Fast Fourier transforms, or Fourier transforms. Some of you will know about fast Fourier transforms. We want to do signal processing as quickly as possible, and the more complex the signal, the more computationally intensive it is. And so quantum Fourier transforms promise a way ahead for real-time processing of extremely complex signal paths. Quantum machine learning. If we can speed up neural nets and the like, then there is real possibility of doing things like medical science, finance, aerospace design. And in fact that's the field that Shoal's currently pursuing. And quantum annealing for optimization. They are the 5 fields that are seen in some of the literature as being the most promising after this many sort of years of work. All right, but limitations. All right. First of all, we can't just take existing algorithms, and this is where the commercial side runs into a little bit of trouble. We can't take algorithms that have been well developed over years or even decades on conventional computers in the commercial world, whether it be finance or health or air traffic control or what have you, and simply put them on quantum computing hardware. They need to be recast, and that's not a simple process. Some of you will be well across the days of parallel computing, where we went to multi-threaded computing, and we had to do a lot of software rewrite to make that work and get best benefit out of that. And so right now there's insufficient maturity in hardware and software stacks for true portability. And furthermore, because the architectures are still developing and competing, different algorithms are suited to different hardware architectures. Many things to do with optimization and annealing, for example, are funnily enough suited to the sort of annealing architecture that the DWave company promotes as its core offering. And furthermore, those of you with a computing background in the deep distant past will recognize this. It's very different from modern conventional computing, where those developing software don't really have to worry about the nature of the hardware on which their software is running. It's abstracted so much that you can just develop for your end purpose without worrying about that. Cast your mind back to the days of machine language and the like, where software developers had to have a pretty good understanding of the limitations of physical computing architectures, and then gradually over time we've abstracted those away. And as I said, our hardware architectures are still evolving rapidly. If you look at the history of the motor car and the history of the aircraft, you go back a century or more, and you will find a proliferation of different architectures for those sort of vehicle types. And within a few decades, they generally settle down to a very small number of archetypes which persist till today. And I think that that's going to happen with quantum computing. I don't think it's going to take decades. I think it's going to take years rather than decades, but I think it will settle down to a small number of key architectures which will be enduring. And again, where are we? We're living with noise and specialist applications, which segue into my practical example. A near-term application that's beyond just large-scale computing. So most of us, when we think of quantum computers, I think because most of the world's large firms that are pursuing this are essentially around supercomputer replacement. Like IBM Q's System 1. That's a way of doing it. There are alternatives. For example, low-cost and responsive remote sensing from space. There's a small satellite, a very small satellite. You can see the approximate measurement on the left-hand side of the slide. It's about 1/3 of a meter in length in the body of the satellite. That satellite's capable of quite sophisticated machine learning-driven radio frequency and electro-optic remote sensing from space of the Earth. And our hypothesis, which we're working, is that adding quantum to this, quantum machine learning will vastly improve how this is done. And of course, the constraints we've got there are limited electrical power and particularly limited space to ground communications bandwidth, because the alternative would be to collect lots of data from sensors and simply beam it all to the ground and process it on a large computer, a large supercomputer or a large quantum computer or what have you, but we can't do that. We don't have the bandwidth, so we have to process it in situ on the satellite. And so we're looking at being able to provide remotely queryable sensors so that you can simply ask the satellite via very, very skinny communications, what it sees, and can it please go and find a particular object, and that object could be a person, depending on the range you're doing it, and it certainly could be something like a ship or a vehicle or some sort of geographical feature. All right, the candidate, and going back to my candidate algorithms list, what are the sort of algorithms we'd use for this? So the practical side of this, Grover's algorithm for searching an unsorted database for complex object matching from a large data set. The quantum Fourier transform for signal processing so that we can pull out clean signal in very, very noisy environments, and think about noise like for electro-optic things like cloudy environments, and quantum machine learning to apply artificial intelligence for rapid learning. We expect we expect this sort of system to be able to learn its environment over time, preferably a very short amount of time, so that it can respond rapidly to changes that it sees and provide value to its owners. And ladies and gentlemen, that's my quick tour through quantum applications. Thank you.
Thank you very much, Sean. I took some notes here. Very interesting presentation. I personally do like a lot the diagram about the noisy intermediate scale quantum, because I've tried myself to use pretty much any quantum computer that is offered today to the clouds, right? Public clouds. And you know what happens when you try to perform a computation, right? Any computation, the type of outcome you get, right? It's noise, it's a result plus noise, right? And that's really but the good thing about that is that things are improving, right? Are improving pretty quickly. So that's great. Thanks a lot for your presentation. So we're going to move forward. We're going to go ahead with the last presentation from Dr. Andrew Housley. So Dr. Andrew Housley is the CEO and co-founder of Quantum Brilliance, a Canberra-based startup using diamonds to build quantum computers that operate at room temperature and are small enough to slot in wherever computers are used today. Dr. Housley is a quantum scientist and engineer with a career focused on designing, building, and operating practical quantum devices. He has worked between Australia, Switzerland, and Germany, and led the experimental diamond quantum computing efforts at the ANU prior to founding Quantum Brilliance. Please, Andrew, whenever you're ready. Thank you.
Thanks, Hugo. And great to be here today. Thanks, everyone, for dialing in. So, yeah, I'm Andrew. At Quantum Brilliance, we're building, as Hugo mentioned, quantum computers that aren't confined to the cloud, but instead are able to be used wherever quantum computer or classical computers are used today. So in a vehicle, in a satellite, or ultimately even in your laptop or mobile phone. And we're part of a growing quantum industry in Australia, where we're taking Australia's research leadership and translating that into world-leading companies. Quantum Brilliance is founded by myself, Marcus Doherty and Mark Lowe, and we're now nearing a team of around 15 people. And I just want to then start at this by saying, you know, when we talk about opportunities for the Australian quantum industry, it's really important to highlight just how critical sustained early support is for any venture, particularly deep tech coming out. And so Australia is fantastic at producing amazing research results, but then turning that into a successful company is something that we as a country traditionally struggle with. And a big part of that is around the kind of ad hoc nature of the access to that sustained support. So we've been incredibly fortunate at Quantum Brilliance. Our success in founding and growing the company has been shaped by sustained support from several organisations, notably the ANU, CSIRO's ON program from On Prime through to we just graduated from the On Accelerate cohort, and then also in the ACT from the Canberra Innovation Network and the Kiln Incubator. And so I want to acknowledge the incredible support from all of those organisations, but then also reinforce that there's a lot of great science just waiting to come out from Australian research institutions, and this kind of support is exactly is a critical enabler for that. So to start with, I'll talk a bit about Quantum Brilliance in our vision, and then segue into how that what that means for the Australian quantum industry more broadly. So quantum computing, as we've heard today, is a leading solution to take us beyond the limits of the transistor. And it's often presented perhaps as a bit more magical, not today, but in the popular press than it is. So it's taking advantage of well understood phenomena, but that are unfamiliar because they tend not to be exploited in everyday devices around us as visibly as other phenomena like electricity. And by exploiting them in computers, this is a new resource that then enables us to solve certain problems much, much faster. And even though we're only at the beginning of our journey, already last year we saw a single quantum processor outperform what was then the world's largest supercomputer. The challenge though is that quantum is taking us back to a mainframe role, just like in the 1950s and 60s. It's going to do incredibly important things, transform certain sectors, but also be fundamentally limited in the types of applications it can support. And this is because of cryogenics, vacuum systems, other complex infrastructure requirements. And so it makes it hard, hard to integrate into the classical computers and hard to reach quantum advantage. So at Quantum Brilliance, instead we're looking to move beyond that mainframe model, and just like how the microprocessor came in the 1970s and really transformed what classical computing could be, we're looking to bring in then what we're deeming or calling a quantum microprocessor. And we're using the extreme properties of diamond as a host material to build our quantum computers around, to create these ultra small scale quantum computers that are able to operate at room temperature without any of those infrastructure requirements of those other systems. So the goal is to, over the next 5 years, shrink quantum down to something that is the size of an accelerator card that you see in computers today, so smaller than a lunchbox. And by going from these room-sized devices that are providing already supercomputer level performance for certain tasks and shrinking that down into that accelerator card form factor, we can then accelerate the pathway to quantum computers doing their key job, which is giving us a box that solves our problems faster. And a key part of that then is having a small box so that you can, rather than having, so that it's operating in the regime of GPUs and CPUs, and rather than supercomputers. So our pathway is then already in the first half of next year, taking orders now and delivering customers quantum hardware that they can own, host, and operate themselves, and then partnerships to co-develop quantum hardware to optimize it for certain applications. So this is this in the box that's solving our problems faster. There's not just quantum parts, so there's a host of classical technologies and engineering, for example, CPUs, GPUs, and other control systems that we can then optimize for certain tasks.
5 minutes.
Cheers. And so what this means is, one, in the context of a supercomputer or a data center, we can, instead of having 1 or 2 quantum computers in the next room, we can now have thousands of quantum computers that are deeply integrated in the racks alongside your CPUs and GPUs. And we can also take quantum out into the world. So you can have it under your desk, or putting it in an autonomous vehicle, or up in a satellite. So how does this then play into the opportunities for Australia and the quantum industry here? So the first point there would be that the industry verticals extend well beyond spin-outs such as ourselves, which are leveraging these unique quantum research outcomes. It includes advanced manufacturing sectors, it includes finance, mining, all the consumers of quantum technology, and the developers of quantum applications. Success for us as a quantum industry in Australia is about all of this diverse group of stakeholders from research, startup, and broader industry coming together and combining our expertise. Now, the great news is that the barrier to contributing to and benefiting from the quantum industry is not as high as you might think. And particularly with Quantum Brilliance's low size, weight, and power quantum processors, quantum can be useful for your business both sooner and in different ways to where you might have been thinking. So we've got great talent pools in Australia across classical technologies in advanced manufacturing, radar, telecommunications, software engineering, machine learning, embedded systems too. So these all map directly to the engineering required to design, manufacture, and operate quantum computers. And it can involve companies building the software stack to control and interface with quantum computers, or designing protocols to improve performance. We can have companies that build expertise in the hardware and software systems integrations challenges for quantum and classical computers, or working on the discovery and benchmarking of applications of quantum computing, like with QXBranch. This requires then access to quantum hardware. It requires quantum simulators, but it also requires a partnership of both quantum experts and the application domain experts. And plays then into this concept that I talked to just before about co-design, where we're optimizing the combination of classical and quantum technologies in our box to provide quantum advantage in specific problems sooner. Now, some of the key challenges to realise the potential that we have in Australia, and it is a very real and very large potential. We've benefited from 20 years of sustained investment in quantum science here. Then the need to bring together these diverse communities and the need for opportunities for newcomers to quantum in particular to experience quantum hardware and drive new ideas. And so these are things that we're working towards in our partnership with Pawsey. So that's setting up a quantum innovation hub, including events like this. And today it's really wonderful to see so many people here today, including people who no doubt are not usual visitors to Pawsey. I think that really speaks about the value and relevance of what we're doing together. And it's also about providing tools to help drive innovation. So we're building towards publicly available quantum hardware in Australia. That's a long-term goal. But in the meantime, we've developed an emulator of our quantum diamond hardware, which we're looking to make available with Pawsey soon. And this is a tool that enables people to start engaging with those activities that I just mentioned, building their understanding of quantum hardware and how to integrate quantum into real workflows. So I'd end with there's opportunities for collaboration with Quantum Brilliance and Pawsey in pilot projects here. And so I'd encourage you to reach out to either Pawsey or ourselves if you're interested in that. And you can follow us on LinkedIn, on Twitter, and find us on the web. So I'll leave it at that. Thank you very much.
Thanks a lot, Andrew, for your presentation. I think we have a break now. Just to summarize, right, going to all these presentations, I think we had, a good summary of, the domains of applications, right, for application for quantum computers, technical challenges we have to address, and we even saw a picture of how a personal quantum computer might look like in the future, right, from Andrew's presentation. So great, thanks a lot.
I might actually just share my screen, Ugo, if you want to have a look and comment on the poll that we just did.
Sure, yes, we can do that.
And then we'll get into the presentation. So this kind of the sectors or application domains that most of our audience could apply quantum hardware emulation technologies. This is quite interesting.
Yes, I'm looking at those. I actually, quite interesting, the smart city, it's small, it's very small, but the smart city scenario planning, that's something that we discussed yesterday, in conversation with other people, but that's very interesting because there are a lot of aspects where I believe computers in general can be used, but that's good. Defense University, government research, that's very interesting. Yes, the one question I would have is about the university tag there, right? What does that mean in general? I mean, there are many, is it research or, yeah, we'll see.
Yeah, we'll keep this open for everyone to continue populating. I think you might be able to go back in there and put in more words if you want to. So if you want to talk more about specific domains to answer that question as well, you're more than welcome to go back and keep doing that. I'll stop sharing my screen now so that we can go back into the event and begin the panel discussion.
Yes, sure. Thank you, Aditi. So our panel will be our presenters, which we have already introduced, and then another couple of people which I am going to introduce right now. So first one is, okay, let's see, where's the thing? Yes. So first one is Mr. Bill Barty. Bill is the managing director of Main Sequence Ventures, CSIRO's venture fund, and he focuses on investing in quantum technologies, artificial intelligence, machine learning, synthetic biology, and data information. Bill has been working with technology founders in Australia in the United States for 20 plus years and has led investments in many multi-billion-dollar companies, including Seek, Altium, LuxSmart, OneBox, and Culture Amp. Bill does have a depth of experience as a successful builder, CEO, and investor, in addition to a deep network of venture and customer contacts globally. And the other person I'm going to introduce is Maciej Sitowski. Maciej is our head of scientific services at Pawsey, but he's also a mathematician and a computational scientist, and he does have expertise in optimization and development of applications on massively parallel and accelerated HPC systems. Maciej is a highly documented author with more than 25 publications in various fields of computational science. And so we're going to start the panel now, and this is really your opportunity to ask questions, right, to our experts. We do have this chat function that you should be able to access from within Zoom. So please feel free to ask questions. In the meantime, I was going to go to this list of topics that we have here, right? So we put together a list of topics coming from conversations and feedback we received from many different sources, right? There is a lot of stuff here to go through, so I will start selecting a few of these, and then we can start from there. We have actually 13 different topics. So just reading through here. Yes. So I would say that maybe we can start with something like practical applications of quantum computing, for example, to weather forecasting, right? There were conversations about, is it viable to use in the future quantum computer for weather forecasting, for example, right? So if any of you on the panel has any insights on these, please go ahead, and it would be great if you could shed some light on this topic specifically.
Well, it's Cathy here. I don't know for sure, but optimization is one of the things that is meant to be able to be managed, as well as manipulation of very large databases. So I must admit, it's one application I haven't seen articulated. It'd be interesting to see if any others on the panel have done that. But I'll take that away too and just ask our climate modelers and our Bureau of Meteorology to see if it's on their horizon. It's a very good question.
Look, the thing is, this is just an example, right, of applying quantum to simulations at the end of the day, right? Because you are solving systems of partial differential equations there, right? So indeed, it would be good to know if there is an application in general of quantum computing to this kind of domains, right? It's not just weather, of course, but yeah, it would be great to have an understanding.
The actual link might be available within the machine learning approach, because we know that, I mean, that's already something which is on the radar for people working on weather forecasting codes. So not classical simulation related to prediction of weather, but also using more modern ways of predicting weather based on the data.
Yeah, clearly. I think there was mention in I think the other presentations, right, about quantum machine learning. Yeah, that I was just referring specifically to simulations here, right? But that's fine. Okay, that's good. So we do have, I think, something about, because we do have here Andrew, right, from Quantum Brilliance. Right, it would be good if we could explain a little bit more about what they are doing with Diamond, right? Because if you look around, I did look around myself, right, for what's available today. If you want to access a quantum computer, if you go to AWS, to Amazon, right, they offer 3 different options. The one that is probably the closest to what I believe Quantum Brilliance is doing is that ion placement technique, right? But anyway, if maybe Andrew can shed some light again on what they're doing with Diamond there, right? And why is it important to have something that works at room temperature, for example, right? This is the kind of question that I guess came through in the past few weeks.
Yeah, sure. Okay, thanks. Happy to. So you're right. Things like spin qubit systems, like trapped ions that IonQ is developing, are quite similar to where we're at. And there's really a multitude of ways to build a quantum computer. All of them at their heart, the core thing is isolating that quantum system from the environment. And so you can do that by removing the environment, so having trapped ions in a vacuum, and then you trap them using electromagnetic fields and lasers. Or you can trap them inside a crystal, and in most cases then, or say superconducting qubits, you need to then remove the noise from the environment by sucking all the energy out, so cool down to almost absolute zero in a cryostat. Diamond is an extreme material that it's, for example, so rigid that actually the vibrations that you'd normally have to worry about aren't really a problem for us. And so you then have this passive trapping system where instead of having atoms inside a vacuum, you now have them inside of a crystal, and you can have them much closer together, and you don't have to actively maintain the vacuum. You don't have to have your lasers and electromagnetic fields to maintain that trap. And so the result is then that you have this thing that is very small, so atomic in scale, and all of the complexity is front-loaded into the manufacturing process. Just like with computers today, it's a complex manufacturing process, but then what you send out into the world, like your laptop, is fairly easy for you to operate yourself. That's what we're trying to do with Diamond. And the key thing is exactly with room temperature, not just room temperature, but room pressure, ambient operation, and simple control systems. It's about simplifying quantum so that you can use it in a much wider range of scenarios than just a mainframe centralized or very controlled environment.
Okay, thank you very much. This is quite interesting because this is both a question that somebody asked from the audience, and I had myself written down here, so that's perfectly aligned. Now this is great. We have a question, another question coming from our audience, directed specifically to Bill Barty. Question is the following: how is COVID-19 and the financial crisis affecting, or if it will affect at all, the development of startups, startup companies, and investment in the field, right? I guess this applies to many other fields as well, clearly, right? Crisis, how is the money going to be spent going forward? But if Bill, you can comment on that, right? Do you believe that the current crisis is affecting in any way what the type of investments that are going to happen in the future in the area of quantum computing or not?
Yeah, it's a very good question. So there will be some effect, but I would say this, that if you have a great company, it doesn't matter when you start it. So you can start it in the deepest depths of the deepest canyon, in the deepest ocean. And if it's a terrific company, it'll get funded. And if you look at a lot of great companies, Google, Apple, all these great companies were started in recessions or financial crises. So the key here is to have a terrific company with a terrific product that solves a real pressing problem. So that's point number one. Regarding quantum and quantum companies, I don't see a slowdown at all at the moment. You know, on occasion, we'll see a pause here and there, but for those companies who've got great solutions, and quantum is such a game changer potentially that there's quite a bit of money going into the system. So for those who have something unique and those where there is an application, perhaps it's real or more near term, I think funding is available. So COVID-19 hasn't really affected the landscape very much. In fact, if we had a usable quantum computer now, we might be able to design better molecules and have a vaccine faster. So I'm all for, let's get the show on the road.
No, thanks a lot. That's actually a very good point, right? It's kind of natural selection, right? So when something like this happens, if you have the best or at least a good solution available, you're going to survive. If you don't,
right,
then that's it. Yeah. That's great. So there is a question I have to ask. This is very specific, but I like it a lot. So the question is the following: isn't the Majorana fermion the best particle to remove noise as it is its own antiparticle? I don't know who can answer this question. The funny thing about this is that I was looking at some story about Eto and Majorana, the Sicilian physicist, right, just last week, because some new information came up about this mysterious disappearance. So, and that's quite interesting. So I don't know if anybody here is able to take on this question. My question, for not knowing anything about the topic, is if this specific particle has even ever been considered in the context of quantum computing. Right, so that's...
I can help a little bit. Maybe Andrew might want to finish up, but Majorana fermions are potentially seen in superconducting materials, and the idea is that if you can get that working in as a qubit, that will have quite low errors in the qubit, and so therefore you won't need as many qubits to be able to get the quantum computer to work, because it's all about probability and management of errors. So if that will work, then that will, and it's often called topological superconductors, is another way of describing that. And if you're able to do that, then you'll be able to really make some headways quickly. But it's still a undemonstrated technique as a quantum computer. But I know that Sydney University is doing a lot of work in that area. But Andrew, so it has to be cooled, which, because it's superconducting, it'd be one which is cooled. And I guess the difference is with the if the diamond qubits are that you actually don't have to cool them. But Andrew, you might want to follow up on some more discussion on that.
Oh, look, Cathy, I think you pretty well nailed it. So I'll leave it at that. Thanks.
Okay.
I think it is worth saying that this is the approach that Microsoft is taking. And I think Cathy stated it absolutely right. I mean, you got to find the particle first, and then you got to make it work, and that's a very, very hard thing to do. So in theory, it should work great, but there's been no demonstration of it yet. So a ways to go.
Okay, thanks a lot. No, this is great. I'm reading through the questions. It's hard to select the one we want to ask next. I'm gonna go with this one. It's about quantum computing and quantum Fourier transform in particular, right? Somebody's asking if it's suitable for large data. So I guess it's probably the same type of issue that was discussed not long ago with a number of people, right? So you were talking about algorithms, right? But then in particular in the area of machine learning, you want to apply these algorithms on very large data sets, right? Petabytes, right, of data. So I guess probably the question goes in the direction of if these techniques we have heard about, like quantum Fourier transform, for example, is something that can be used today or in the near future on actual data sets, right? I guess probably that's what this question is about, I guess. But I don't know if anybody can help with this one.
So it's and other people on the panel will have additional expertise they can bring to this, but it's very much one of the real challenges with quantum at the moment is the kind of data input output overheads there. So some of the best framed problems for a quantum computer have a relatively small number of input parameters, a relatively small number of output parameters, and then do something incredibly complex in the middle. Or it's around, I guess, manipulating data that's already in a quantum state, for example, a quantum computer integrated with a quantum sensor, things like that. So when we're starting to look at big data sets, it's that you can't go and take that entire data set and just plonk it in the quantum computer as is, particularly for near-term devices. It's then breaking up that data set and breaking up your computation into very small subsections where you identify the particular parts of that the quantum computer can provide a speed up, and then you're using a classical computer for the rest, because there's things where a quantum computer provides that whole world of speed up, and areas where it really doesn't help at all. And so the solution the future of computing is not quantum replacing classical computers, but quantum augmenting it and working as an accelerator closely alongside, still having CPUs and GPUs and other systems. And so bringing it back to that big data problem, it's around how you break that up and take advantage for particular parts of that to send that to a quantum computer.
Okay, thanks a lot. So that this question comes from the radio astronomy community, right? So, and I guess that's why we're also looking at quantum here, right? So there is a way to process this huge amount of data that will come from the SKA experiment, for example, the telescope going forward, right? So anything that can help clearly would be much appreciated. Thanks a lot. Let's see here. So I do not see question that might be asking coming from the audience, unless I'm missing something here. There are quite a few questions that have been asked, but I do have a question. One of the questions that we collected here, right, on our list. So this is about specifically, right? This question would be, directed to Sean. I am myself personally curious, right? So, about what does it mean to build a quantum company today, right? A quantum application company, and even resell it, right, to someone else. What does that mean in terms of experience, right? How do you go about that, right? From inception to exit, right? Exit strategy and everything. How does that work?
So thanks for the thanks for the question, Ugo. When we started QBranch, because it came out of a complex systems engineering company, our work in Shoal is all about understanding end user needs, understanding operations and problems, and how to provide solutions to problems. Far more than it's about understanding the specifics of any one technology. It's about the understanding how you can apply technology to problems, and problems that you've understood properly. That's a key issue. And so when we started QBranch, we essentially did the same thing. We said, well, there's going to be a number of companies start doing hardware, and funnily enough, within a couple of years, there were, and now there's probably a dozen smaller companies doing their own hardware. For example, Rigetti. I mean, Rigetti is actually quite a small company at the end of the day. And then we knew at some point that the global giants, the likes of Google and IBM and Microsoft, would lumber onto the scene and deploy hundreds of millions, if not billions of dollars to try and win that race. And that's exactly what happened. We said, well, we don't want to get squashed by elephants. So what we want to do is understand the problems that these things can potentially solve, because ultimately that's where the value is. And if you look at classical computing as a financial example, companies like Intel are very large. They have huge revenues. But if you then look at the software companies, Facebook, Google, etc., their revenues are far, far bigger, and their profitability is far, far higher. And so where do you go with the business? It wasn't just that we actually had significant investor returns eventually. And so we went for the application space. And so the process really was around, okay, where should we start? Based on the attractiveness, based on the three factors. One, the attractiveness. Secondly, the assessed tractability at the time, noting that back in 2014, you're making some assessments about what might be tractable, which turns out later on to be either true or very extremely expensively untrue. And also the resources available to the company, both in terms of money, but also more importantly, far more importantly, the people involved in it and the pathways they could provide to us. And we started in the finance sector because most of our investors were from the finance sector. The likes of, there are quite a number of Macquarie Bank executives invested in, what was QBranch. There are others from places, like Hong Kong and the UK, the US, many from Australia. And so we had pretty good pathways into some of the world's major, finance firms. And so that's where we started. And then later on, we started to branch out into things like pharmaceuticals and, oil and gas and the like. But that was based on early success and often on references from that. So in many ways, it's not stunningly different from doing other businesses that are broadly of this type. I've been involved in a few in my career. And in fact, one of our management approaches was don't change too much. Like the novelty was clearly in the quantum computing. Would it even work? Because we started this journey in 2012 we had access to the one working DWave computer available in the world, which was Lockheed Martin's, which was owned by the Joint Strike Fighter program. And we were given access to that and said, well, what can we do with it? Can we see a pathway? And so that's the novelty. Don't make the business model itself novel. Let's go off and develop the applications. And that worked pretty well, to the point where, you had a company which has got significant investment now, Rigetti. I mean, it's a small firm, but it's got significant investment. Finding that attractive as an enabler and a force multiplier for itself, because it puts Rigetti's pitch to the world is that it's a full stack quantum computing company. And so if you're a full stack company, you need the application software at the top of that stack. And that was us. I hope that answers the question.
It's great answer. I mean, it answers everything. It's I also understand very well, right, why you did focus on software, right? Think about Microsoft, right? What happened to Microsoft? That's really,
yep.
At the time, right, it was the same thing. Everybody was investing on hardware and they invested in software. Also, software, you know, if you're thinking about implementing new algorithms or whatever, all you need, indeed, you would need to access a quantum computer in the end. But a simulator might be good enough, right? Because you're really proving, you know, that the algorithms work, or would work on an actual quantum computer in the end, right? So that's great. No, thanks a lot for the answer. Related to what I just said, I think there was a question, or probably not here, but anyway, I'm gonna go. Yeah, okay. Next question is really about having a simulator versus an emulator available, right? For dealing with this kind of problems. I think in Sean's presentation, if I recall well, he was specifically mentioning these things, simulator, emulator, I forget now. Quantum Brilliance clearly can provide today a quantum emulator to whoever is interested, right? So I want to have an understanding what is the feeling for, or what you think is the need today for accessing an emulator versus a simulator, or an actual supercomputer, right? So why would we need, for example, to access an emulator today, right? If somebody can say something about that, that would be great.
Well, I might get the ball rolling there and then throw that to the rest of the panel. But so we see in the kind of hierarchy of complexity is, best case is you've got the quantum computer, and that lets you do all the things that you wanted to do. And this is around more than just developing applications, but also the whole suite of being able to take advantage of quantum computing is developing applications. It's about training workforce. It's about understanding how to integrate quantum into classical systems. And it's about understanding how to optimize and best make use of quantum hardware, particularly in the near term, whereas Sean put so well, you got to take a lot of spares with you because the wheels keep falling off. So in that kind of hierarchy of complexity, I'd say a quantum simulator is something that enables us to understand in a pure sense what the absolute limits in a perfect world of a particular algorithm might be, and understand where that's going to play and kind of rapidly explore there. And emulator is then the next step, which is enabling you to understand then with some more constraints around the real world, what the performance of a particular thing might be. And it's focused then on a particular hardware design or geometry. And so because a lot of the performance of real systems is then severely limited by things like connectivity, the fidelity of the qubits, noise sources within them. And the other side of things is then where we talk to big data problems, is that end-to-end workflow around how you interface to a quantum computer, how you then put data in and get data out, and how you're able to integrate that into the broader classical systems that you need to operate with. And that's kind of the sweet spot for the quantum emulator.
Okay, thank you very much, Andrew. I will add to that in supercomputing, but many other domains as well, right? What we do is to research the performance model, right, of whatever application we're dealing with, and that thing is tied to the hardware, right? So understanding how the hardware eventually works, right, is very important. So if you have something that emulates the actual hardware, it's easier to come up with a proper performance model, which you can then use when you are developing software, right? That's my view on it, but that's fine. Okay, thank you very much.
I think I would like to add something. Yeah, I would like to add something as well. because I also seen a couple of questions, and also one of the breakout rooms topic is quantum computing versus classical computing, or versus supercomputing. I think we will actually going forward, and it was already mentioned by our speakers. Going forward, we will see actually those being used together, and so the whole idea of and the exercise that we are having now with Quantum Brilliance is to understand how that will fit. So how things like quantum emulators into a supercomputing ecosystem, and that's looking at things like what algorithms can take advantage of it, what it actually means to run an algorithm on a quantum simulator or an emulator, and how to integrate that in a type of hybrid approach where you use the quantum simulator as a maybe something like a QPU, which was already mentioned, so like an accelerator to run some parts of the calculations. And that's actually something that is it is well known worldwide that even for the big examples of the use of quantum computing available worldwide, I will use the Google supremacy paper example just because I know that it's a bit controversial, but that particular one was actually showing that, again, if you want to achieve big calculations on quantum computers, part of the calculations will be also done on classical computers. And in that particular example, Google also used one of the biggest supercomputers they had available at that time to achieve that result. So yeah.
Okay, thank you, Maciej. I think we have a few questions that we must still be asking, but it's 3:30. I'm going to ask this question, which I actually wanted to ask myself, but now it's coming from the audience. So the question is to Quantum Brilliance, right? The question is really why you chose diamonds, right? Here they're making the point that diamonds are expensive. And so when we talk about the price point, right, comparing a QPU with CPUs or GPUs, then you might not really have a real advantage, right? I will expand the question by also asking a related question. So in these days, you can grow diamonds in labs, right? You can have synthetic diamonds being mass produced, right, if you wanted. So this is the main question. Why did you choose diamonds? And in particular, do you see any problem with the price point, right, of such a solution? And the other question, which I'm asking myself, is, can you use synthetic diamonds, for example, right?
Yeah, so thanks, Hugo. It's a really good question. Where to start? So the quick answer around synthetic diamonds is yes, we do prefer to use synthetic diamonds. We've simply got more control over that. And so really it's then thinking of it like a diamond wafer, in the same way that you buy a silicon wafer and then you perform some kind of proprietary process on top of that to create your classical computer here. We're then doing some value add processes to a diamond wafer. They're a bit smaller than a wafer these days, but and then creating our quantum bits inside of that. Why? So once synthetic diamond is actually nowhere near as expensive as natural diamonds, and the price is really volume driven. So as we create a market for diamond-based quantum computers, there's every scope for that price to plummet. And the amount of diamond that we need to use is also quite minimal. So with atomic scale qubits, remember we're thinking about 50 qubits already performing at the scale of a supercomputer for certain tasks, and in a error-corrected mode or in a high-performance mode, your performance almost doubles for every qubit that you add. And so in diamond, in a cubic micrometer of diamond, you could even have 1,000 qubits quite easily. So the material cost is not a key driver. And why diamond? It's really because of the extraordinary properties of being able to operate at room temperature. And so it provides by far the best performance of any solid state system in terms of quantum properties.
So this is a question actually coming from me. So we talked about the why diamonds, but still related to how competitive this QPU solution would be in comparison to other classical options, right? In terms of power consumption, right? Because we know very well how much a GPU consumes pretty much, right? It's 300 watts, give or take, 250, depending. But so how much would you forecast? I suppose it's just a forecast, right? You cannot really probably have the actual numbers, right? But if we're talking about putting a QPU inside whatever system, would that thing have a comparable power envelope or not? What are we talking about here?
So for the QPUs that we're looking to develop at Quantum Brilliance, it's on the order of a few hundred watts or even less, really driven, so potentially even sub 100 watt, really driven by the power consumption of the classical control systems that we put around it. So the diamond itself is then has no power draw, which is quite a contrast to, say, a dilution refrigerator, which superconducting qubits would require, like IBM and Google, might be 10 to 25 kilowatts of power draw. So the power consumption can be really quite low, and is then driven by how you want to optimize your box for solving a particular problem. And so how much GPU power, for example, you might want to put in that, or CPU power. And that's really what's going to drive it.
Okay.
Can I just add, there's also some work that's just recently been published by Andrew Dirac and his team at University of New South Wales, where they've showed qubit behavior which has been cool but not requiring dilution refrigerators. And you can actually get these compact cryocoolers now, which are quite low energy. So there's a lot happening, and I think at the moment we've seen a bit of a dichotomy between the big dilution refrigerator, very complex system design with packaging that really is looking like, sort of almost like the first computers we have with Syriac and all that, where they had lots of valves and things joined together and took a whole room up to do something which you can do on probably on a little basic calculator. But these days it is. But what we're seeing though is as we're getting to understand scientifically what's possible, device development being improved, and also designing devices which are able to take some of those noise issues into account, that because it's basically thermal noise that adds to that increase in error problem, and so therefore requiring to go colder so you reduce your errors. That looks like they're sort of maneuvering their way through that. Not perfect yet, but I think what we'll see is in time really new concepts coming through, just like the diamond qubit is something which is really revolutionary and a real left field thinking. I think we'll probably start seeing other things coming up in the solid state as well.
Okay, thanks a lot. Actually, that's a very good insight, because actually my question itself was kind of reformed, right? So the reason for which I was asking that is because what we normally do with classical computers is that we calculate the efficiency in terms of watts per flop, right? And this is very different. This is a very different environment. So, even if it consumes kilowatts compared to hundreds of watts, right? But does solve the problem in a fraction of the time. That's clearly, it's not the same thing, right? But I was just wondering, if there something was happening in terms of minimizing the power consumption there. And it seems it is.
So, I mean, just in superconducting electronics in general, there's a big argument between MIT and Northrop Grumman about just having a high power computer, which is or exascale type computer, but it's done with superconducting just regular classical qubit bits, and whether or not the cooling, when you take the whole energy cooling into account, whether it actually is more energy efficient or not. And it's really interesting. There's quite some arguments when you go to these conferences as to whether they, sort of MIT are basically saying that you don't get energy savings, while Northrop Grumman are saying you are. So it's actually an area where it's not settled, and there's some interesting dynamics.
It is. You know, thanks a lot again. So got a couple of questions here. So one question which has been there for quite some time is yes. So yeah, I'm reading the question. So the question is, what time frame do the panel feel that a quantum approximate optimization algorithm running on a noisy intermediate scale quantum computer, so I guess current generation quantum computers, will be available? The question, which is actually on the chat, right, goes on saying that this person is working with a South American company which does have a freight optimization solution almost ready. Yeah, so again, question is about by when would you think that this, you know, a natural quantum approximate optimization algorithm running on a current generation quantum computer might be available? And I would say that given the type of company, it might have to do with, you know, optimizing, you know, some operation research type of algorithm, right? But anyway, so yeah, if anybody can shed some light on what you think about this specific problem, right? Yeah.
Sure, Sean, here I might start. I'm just rereading the question in here, which is quite a while ago.
Yes.
Presuming that the South American company has a freight optimization solution almost ready in conventional computing, I assume the question is, how could quantum computing be applied to improve that situation? Assuming that's the case, that's actually not. A few years ago, that would be a real challenge. Right now, that's actually fairly easy. A number of companies like Amazon offer essentially QAS, quantum computing as a service. You can pay money with your credit card, and you can access several different architectures. Actually, I know Rigetti's architecture is available on the cloud, and I think there's at least 2 others, perhaps more. What you need is simply a person or people who are capable of sort of using that. You've done the hard work. Well, that company's done the hard work already. Understand the problem. Understand what you're actually trying to optimize. Then how to apply the technology is just essentially a trade study problem of, all right, I've got conventional silicon. I've got GPUs. I've got 3 or 4 different types of quantum computing. Let's try those out. And in fact, I can see someone's come up with the list there. And then, you know, perhaps you can actually compete and try them all, and even design yourself a roadmap of, we're going to start with this and then move to that. And if that matures, we'll move to that. I could see a pathway through. But again, to repeat, I think the major issue, assuming they've done it properly, of course, is that the problem has been characterized in a computable form. And now that computable form can be applied to the various technology choices to see what adds value. Thank you.
Thanks a lot for your answer. Actually, that would have been my answer too, right? Because you can go to AWS today, 3 different architectures running on one of those, right? I did check that thing 2 weeks ago, right? So when they made the announcement, probably last week, it really does cost around $10 to $20, right, to run on an actual quantum computer, right? Some I would say mid-size type of computation, right? So it's something doable. Again, good point about characterizing your algorithm, right? And your problem in a way that can be digested, you know, by a quantum computer. I think that's the challenge, right? So that's the main issue, I would say. But
so I was wondering if I could just add to that, and it'd be interesting to hear from Bill about this as well, is one of the things you're seeing with the whole concept of anything to do with things quantum is the evolution of different business models. And I think that's going to be just as important as the technology development as well. And how we're seeing, you know, for example, toy or the different access to quantum computers for people to have a go at, seeing simulators being set up, going through looking at, say, for example, Andrew's design of having something which is really compact that can then go into satellites or into into sensor systems. It's really, it really is going to be application driven as to what it might look like. It's not as though there is a single quantum computer. I think the idea is that there's going to be whole different sorts of types of computational things using quantum physics as the basis of it. And so therefore it's going to be quite different to the way we think about just classical computing, where, you know, we've got probably all of us on us have probably got a huge number of computers on, from Fitbits to, you know, mobile phones to the computers we're using, but they're still all based on, you know, some you know, sort of classic Intel type infrastructure or architecture. I imagine that we're going to be seeing the evolution of different sorts of architectures, approaches, depending on the application, and also the business model that makes sense to deliver that. Because it's not only that, it's not only just, you know, setting up the company and that, but it's also that access, and that, I think that's going to be really interesting to see. But it'd be interesting to hear from Bill about what he sees as that way we're going to see business evolve in time.
Yeah, just a couple of thoughts. Thanks, Cathy. So, you know, most of the quantum computing approaches these days seem to involve refrigerators and, you know, Dill fridges and things like that. And, you know,
Oh, he's gone.
hello.
Quiet.
I think Bill just froze.
Hold on.
Yeah.
you can, as we've heard many of the speakers and say, and it's Ugo says, you can go to AWS or Microsoft or Google or Rigetti, and you can rent some time on one of their machines and pay for it almost on a per per qubit basis. So that's one way. The companies, companies that are also developing quantum computers are also taking the approach that they're consulting with clients who want applications built. And so it's an effort where you educate the customer about how quantum computing can help them, number one, and figuring out where it fits in their business, while at the same time that work informs your product roadmap, if you will. So it's a combination of sort of a consulting / hardware sale to get to the point, where one of these architectures works. In Quantum Brilliance's case, because they don't have any of this big refrigeration and all of these cooling things that are necessary in order to make the machine work, then you can see where you can build, where they could build, small units, proof of concept units, send them out to, to customers, and as they've done, I guess, with Pawsey here, almost as a, as an NVIDIA card where you have a coprocessor. I know that's a bad analog, but where you hand part of the calculation off to the quantum computer, which does some optimization and then passes it back to the classical. So that whole sort of classical quantum interface is going to be quite important. The algorithmic developers, they're developing algorithms that they're then selling and using to customers for money, almost like a software company, almost like a software as a service company. So it's a whole stack of different business models, anywhere from consulting to renting out time to selling the machines to selling software as a service, depending upon where in the stack you actually fit. At Q-Control, where we're an investor, for instance, they sell their solution as software as a service to suppress errors in machines. And so there's quite a few business models out there, depending upon where you are and what your need is.
Gee, Bill, Sean here. I was going to say that the coprocessor analogy is, in fact, I think, a very good one. In that the control system for a heterogeneous computing environment will decide, okay, this particular part of the problem that should run on a GPU, that particular part of the problem should run on a Quantum Brilliance coprocessor, and so on and so forth. And I can see that's how quantum computing, to an extent, is going to find its way into the mainstream.
Yeah, and Sean, I think you were involved in some of the CBA work at one point as well, or
Correct.
About it. So I would be interested just in your comment about the business model around the CBA stuff, just so you can maybe illustrate how a large company thinks about this.
Sure. In fact, I put a hyperlink on the chat to everyone, which goes to a press release on CBA's website, which tells the story pretty well. But essentially, CBA and this was, we started in the finance sector. I said that before. CBA and a number of other companies of their ilk, large banks and investment houses and hedge funds and the like, were looking at quantum computing as not just the way of the future from a positive perspective, but as a real competitive threat to themselves if they didn't get sufficient understanding of it. They were worried that they'd be gazumped by others. And so many of them made small investments to at least find out what was going on. CBA back in 2016, or I can't remember when we started it actually, because this press release is April 2017. I think it was about 2016. We convinced CBA to spend quite a large chunk of money on building a quantum simulator, and not something to emulate so that quantum computers could be developed or whatever, which is another use for an emulator. But for a simulator, it's to throw it to the applications people at CBA, the finance applications people, and say, all right, go play, go try things out, go see what might be useful to you, and then those people can advise bank management on practicality, timeframes, what applications might be more valuable versus less valuable, and therefore what investment path the bank could pursue. There are other institutions that we dealt with which did broadly similar things. CBA is the best example because they published it online and the case study is actually there and only a sort of one web page. It's very clearly written. And so I'd encourage you all to go and have a look at that and see a way that an organization can do it. Now, you can do it now. We had to build a simulator for them. You can do essentially the same application exploration now, online, via the likes of AWS with the 3 or 4 or 5 architectures available today. I can see some commentary around how cheap things are and not cheap things are. I assure you from an investment perspective and a construction perspective that paying a few $1,000s to try out some theories is incredibly cheap compared to what you would have to do otherwise. If you had to raise your own team even, people are going to cost you, if you had to get an engineering firm in to help you, that's going to cost you $10,000 a week a person, at least. So being able to play around for a few hundred or a few $1,000s is, in my view, very, very cheap. And if you're an institution, well worth the investment. Even if it convinces you that you don't want to become involved yet, it'll save you expending funds that you otherwise might. Thank you.
Thank you very much. Sorry. Who was?
I also wanted to add to this one comment to the discussion around treating a quantum device as an accelerator. This is actually something that we as a supercomputing center are interested in, especially from how then you can actually use it for current applications. Let's say that we find an algorithm which can be accelerated on such a device, but then if we have multiple of those devices, what it actually means to parallelize a larger application on such a hardware architecture. So it's actually something that opens a lot of possibilities and raises so many interesting questions for us as people working in a supercomputing area that we are looking forward to experiment with that.
Okay, thank you, Maciej. Just one comment about what Sean said and about one of the comments we received about the cost, right, of running on AWS. So first of all, what Sean said is absolutely correct. It applies to Pawsey as well. If we have to pay a few $1,000s, right, to try out a new technology, that's nothing, right? Or that's no problem. But about the specific numbers I'm seeing here, right, they are absolutely correct. But AWS came up with some new models, right, for charging people for the quantum computers, like I guess 2 weeks ago. The numbers are very different now. Clearly, like with any cloud providers, you have to be very careful in the way you forecast, right, the expenditure, because it's very hard to understand when you start, again, on any cloud provider, how much the thing is going to actually be costing to you in the future, right? So that's something to take into account. But the number, in particular about IonQ, the numbers went down a lot, right? So that's it. I think we have time for just one additional question, probably. Let's see. Stop going. I'm gonna just scroll down to the last questions.
Hugo, there's one about prerequisites for career in quantum computing.
That's correct. That is correct. I just called that one right now. We can probably address that, but I think I lost it again. It was scrolling down. So if you want to go ahead, you can just read and answer the question.
Sure. So, I mean, I'm sure the other panelists will have some great opinion or things to add to this. The key message from my point of view would be there's definitely a need for people with PhDs in quantum computing or quantum science and experiment and theory in the industry, but that's absolutely not a prerequisite to come in and add value. And at Quantum Brilliance, one of our actual key hiring decisions was to also hire people, deliberately go out and find people who have no quantum experience, but who focused on really nailing other parts of the engineering chain. So, and this comes, I guess, from my background. As we move from a science to an industry and an engineering set of challenges, we go from academics in the lab where you're a 1 or 2 person army and you have to do one of 20 things or 20 things all yourself, to then bringing in people who really nailed machine learning or really nailed embedded systems and FPGAs or other parts of the stack, microwave engineering perhaps. And these people don't have to have any background in quantum to come in and work with us as part of a diverse team and really add a lot of value. So and this then going to organizations as well, this much broader idea that I was trying to paint of the quantum industry in Australia, that's not just about startups led by quantum scientists, but also includes advanced manufacturing, includes machine learning companies or finance banks that are looking to engage with quantum computing and can either feed in and help us build the technology, make it work better, or then work with us to find applications for it and create that economic benefit. So it's a very broad range of people. We like to say brilliance is really the only prerequisite.
Can I give some specifics? So University of New South Wales, for example, has just announced last month, I think it was, a degree in quantum engineering and quantum computing, or quantum engineering, a bachelor's degree. New South Wales government's just funded what's called the Sydney Quantum Academy with the aim of developing the workforce of the future. And that's including things from TAFE-trained people who are able to manage cryogenics. We have lots of air conditioning engineers, but that's not quite cold enough. So we need to go down a couple of 100 degrees to get to cryogenic engineers. And that's actually like hen's teeth around the world. So that's for particularly people who are more technically interested. That's a real workforce for the future, because regardless of what computer takes off, quantum computing and quantum devices will still have a level of cryo-engineering with them. And I know other universities around Australia are really looking at how they can have master's degrees and a whole range of things. And I would imagine that the micro-credentialing that universities are looking at potentially setting up, hint, hint to the university people online, is a really great opportunity to look at what you can offer there, especially since I know the government's really keen to see what universities can do to have that quick turnaround of our workforce of the future. So watch this space, I think. I think we're going to be seeing a whole lot of, not quite continuing education, but that micro-credentialing so that people can add things on to their current expertise, because it is quite different. And then, of course, we're very lucky that Australia invested in the Australian National Fabrication Facility, which is the nodes all around Australia, which are for making devices. That's my background, is device fabrication. And the fact that we've got world-class device fabrication and all the, there's so many different universities around in each state that are actually developing expertise in what it takes, not just with that, but also the packaging, the systems integration to be able to make stuff is phenomenal. And I think, from my perspective, really proud that we've actually got that right. And it's shown how, collectively you can end up with some really good infrastructure and also training programs that are bringing through that. And we're seeing it sort of all coming together. I just hope that we can keep working in that collaborative, organized way and make this turn into something pretty special.
I'll just add one, 10 seconds here. So inside some of the companies I've seen, you have a range of PhDs in quantum physics, to engineering, to software engineering, to marketing, and on the physics side, there's both experimental and theoretical. Software side is really taking the information that the quantum physicists come up with and translating it into software. So algorithmic development, lots and lots of different skill sets are needed inside these companies. It just, as Andrew said, it's not about what you can do, and it's not about what you've done, it's what about you can do. So.
Yeah, I would add to this. So yeah, quantum computing devices are quite new, but actually quantum computing algorithms are not, right? So the Shor algorithm that was mentioned during today's talks, I think it dates back to 1994. Yeah. But it's as a mathematician, I need to add just this thing that yeah, quantum computing algorithm design is a beautiful area, and it's very well defined. So this is for sure a field where a lot of improvement can be done, and I would suggest to look at that area as well.
Thanks a lot, Maciej. Unfortunately, we have to close the session. There are a lot of interesting comments coming in, and that's it. Again, we do have to close session right now. Thank you very much.
Thank you, go.
And yeah,
Thank you.
Bye bye.
Thanks, everybody.